Hello, welcome to Science for Alaska lecture, Lasers in Alaska. My name is Rich Collins. I'm a professor in the Department of Atmospheric Sciences and the Geophysical Institute at the University of Alaska, Fairbanks. This is a re-recording of the last lecture of the series that was originally given in January 26, 2013. And as the last lecture of the series, Lasers in Alaska, I wanted to take a moment to thank Stevie Siebert, Amy Hartley, and Kaz Alvarez for the work they had done in organizing the lectures. And today's lecture is being recorded by Andy Cummins. So today I wanted to focus on three ways in which lasers are used in Alaska. The first slide shows the Lidar research facility at Poker Flat. Lidar is the light detection and ranging laser radar, if you will. And it shows a green beam heading up into the sky, and we look at the echoes from the sky to measure temperatures, clouds, and chemical species in the atmosphere. And today I want to pick three topics that I want to share with you in this lecture. And those are, I want to talk about noctilucent clouds, which are sort of a grand National Geographic type of natural phenomenon that is associated with climate change and that you in Alaska can see. I want to talk about volcanic ash clouds and the work lasers do in validating ash plume models and the detection of ash as it drifts in the airways in Alaska. And then finally I want to talk about LIDAR and lasers and how that's used in terrestrial mapping. This is a really big deal in mapping the state, mapping pipeline corridors. It has a lot of interest. It's even being used in real estate work. I have not done direct research in that area, but I've been following it, and it is a major economic activity in the state now, and it has revolutionized surveying, and I'll talk a little bit about that at the end, and if you have any questions, you're welcome to ask them at any time. So, just to start, to give you a feel for how LIDAR is about taking lasers, which are very bright, and usually one color, and using them to detect things in the atmosphere. And the simplest example I can give you is detecting cigarette smoke. And as you can see, as the cigarette smoke drifts through the beam, it scatters and reflects light very effectively so that the smoke cloud appears very brightly in the laser beam. And this is exactly what we do with LIDAR. We put an intense laser beam into the sky and we detect clouds, aerosols, gases by how they scatter that light and create a bright echo in our telescopes that we then detect electronically. And so starting with noctilucent clouds. Noctilucent clouds are night luminous clouds that are visible at midnight in Alaska in the last week of July and the first 2 weeks of August. And these are clouds that form over the pole. They're not visible during the day, they're very thin, but we see them as the sun sets and then illuminates them from below and scatters the light toward you. There's a very unique geometry for how this works, and if you go outside at 2 o'clock in the morning, which is solar midnight due to our time zone in August, you have to look for a while to realize that you'll see a cloud to the north that is generally getting brighter as the sun sets deeper and deeper below the horizon. This time of year the sun is getting maybe to 6 to 10 degrees below the horizon. It's the beginning of August. The aurora is just becoming visible again. And these are ice crystal clouds at about a height of 50 miles in the atmosphere. And I'll just show you a couple of images of them to give you a feel for how they look. So here's an image from Poker Flat looking north, standing on the roof of the LIDAR lab looking north. And you can see that they're very, very bright white. And this is partially because they're very small particles. They're about 100 nanometers. And so I just want to hold that slide for a minute and jump to a video we have that shows those clouds as you would see them in real time. This is in the early evening looking north before the sun sets. Let me go to the start and let me just talk a little bit about what you're seeing. You're looking at Caribou Creek to the north from Poker Flat, and you can begin to see that there's striping in the sky through here, but there's no super obvious clouds. But as I speed up the video. This is a 2 hours of video. I'm just going to speed it up. You can see that as I speed up the video, you get swirling clouds becoming much more obvious as the sun sets. This is now at 11:30 at night. And you begin to see stippled clouds across the sky. And I'm just going to speed up the video quite quickly. And you can see those clouds moving across the sky as the sun sets. And you can see the variety of cloud structures across the sky, and small wave patterns and large wave patterns in the clouds. And in fact, the clouds are of interest in themselves, but they're also of interest because they do such a good job of revealing the waves in the atmosphere that are part of the general circulation. They're also of interest because they tell us about water vapor and cold temperatures in the atmosphere, which I'll talk about in a minute. So let me go back to the presentation slides. And so let's talk a minute about what we're actually doing with LiDAR. With LiDAR, as I showed you earlier, we have a laser shooting out into the sky, and then we have that light coming back into a telescope through some optics, optical filters that only let one color through. So for example, if I'm using a laser that's using a bright green beam, then I'm going to match my optical receiver to only transmit green light down to my detectors so that I get an electronic signal back from the optical signal and the echoes that go, optical echoes that come back. The original LiDARs employed World War II searchlights because there was a huge, before lasers were invented in the 1960s, searchlights were used in World War II for high altitude bombing to detect high altitude bombers, and there was a lot of technology using searchlights. So the original LiDAR systems didn't even use lasers, they predate lasers. And then two students working at Poker Flat, Tao Ho and Tim Stern, in physics and electrical engineering. So the lasers that we have at Poker Flat are big benchtop lasers, about this big, with flash lamps that we put high voltage through, and the flash lamps glow. And then we have very precise crystals, neodymium YAG, that then when flash lamps, you discharge a current through the flash lamp, it fluoresces a an industrial ruby rod, and it creates infrared light that at the last minute we turn into green light by doubling the frequency. And part of what makes lasers work is that you have these very intense optical fields. The laser is the brightest thing in the sky when we're making measurements, because the lasers we're looking at Poker Flat have about half a joule of energy in every pulse. Each pulse only exists for 10 nanoseconds. So the peak power in these laser pulses is on the order of megawatts. So if you synchronize yourself to the laser firing, it's like a strobe light. You are seeing a very intense light source and very intense echoes, even though there may be other light sources in the sky. And so unlike the all-sky camera work with the Aurora, when we do LiDAR, we could be sitting in Manhattan measuring the sky with all that background light, because when we look into the sky, we only look into the sky when a laser pulses on, and at that moment the laser is the brightest thing that we see as long as we're synchronized with it. To give you an idea of what laser echoes look like, this is the echo strength with height. We see initially we have so much echo that if I was to let the signal persist, it would go off the chart over here to my right, and this is a log scale. So I would be completely overwhelmed or blinded by the strength of the echo coming back from low in the atmosphere. What I'm interested in with noctilucent clouds are the echoes coming from higher in the atmosphere, from about 25 kilometers or about 15 miles high. And this is the echo from the air itself, just getting thinner as we go up in the atmosphere. And then suddenly we get this extra echo from a noctilucent cloud. And it's exactly what happens to you in Fairbanks when you're driving with your high beams in the winter, and you're driving along and you're using your high beams and you're seeing the road, and you come around the corner maybe into a little valley, and there's some ice fog, and suddenly you're blinded by an extra echo. Well, that's what we have here, the extra echo associated with cloud particles, which is much larger than the air around. Here's the air echo around it. And so the way that laser radar works, all laser radar works in all the applications we'll see today, is it's an onion peeling experiment. In the sense that we send an echo, a laser pulse into the sky, and it echoes back. The light that echoes back from the lowest part of the atmosphere comes first. Then the light that travels further echoes back, and the light that travels further again echoes back. And so we have a relationship that we have a round trip time on the x-axis, altitude on the y-axis, and a pulse travels out and back in time, out and back in time, out and back in time. If I allow my timing for the first interval, I can say I've got an echo from this region of the atmosphere, then this region of the atmosphere in the next time interval, and then this region of the atmosphere. And so I peel the atmosphere with height and work out a profile as if I'd launched a weather balloon and sent the weather balloon up drifting through the atmosphere. But instead, I'm sitting at the ground sending out light echoes, light pulses that echo back and give me a profile with height up through the atmosphere without me having to launch a weather balloon. And that, in a sense, what LIDARs are. They're optical weather balloons. So just to give you an idea of numbers, I know that every time you show an equation, you lose half your audience. I think there's only 2 equations in the talk, so I'll lose half my audience once and half again, and only hold on to the bottom quarter of my audience. But I just wanted to give you an idea of how LIDAR works. Some of the other speakers had got into the math of what they did, and Amy suggested I give people just a small flavor for the math. The echo, if the echo that comes back from the sky depends on 5 factors. It depends on the sunlight and starlight in the sky, and I'm going to ignore that for a minute. But let's just talk about what happens in terms of the LIDAR system. In the LIDAR system, we've got a laser and a telescope, essentially. And the echo that comes back from the sky depends on how bright your laser is, how much the energy of the laser pulses you have fundamentally. So if you can put out higher energy laser pulses, you're going to get more echoes back from the sky, and you're going to be able to detect sparser and sparser things. That's actually quite limited. Laser technology can be quite limited in what kind of energy you can get out of certain technologies. You can't just make huge energies come out of industrial rubies. At some point the ruby will crack because there's so much heat being generated, you'll actually burst the ruby. So there are limitations there. It also depends on how shiny your target is. Is what you're scattering from sending back a lot of light? Is it a very shiny ice particle? Is it a molecule of air? And so it depends on what you're trying to see in the atmosphere. It also depends on the efficiency and the transmission of the atmosphere. If we have low clouds on any given day, then we're not going to, all our light's going to get lost in those clouds, and it's not going to get transmitted high into the atmosphere where we can use it to measure noctilucent clouds. Or alternatively, as we'll see, if you're looking down in the middle of summer in Fairbanks, and you're trying to measure the ground from an aircraft, your transmission can be reduced because of the leaves on trees. You might decide to do your experiment when there's no leaves on the trees, and we'll talk about that a little bit when we talk about terrestrial LIDAR. The last thing we want, it also matters to how close you are to your target, and that's why many LIDAR people go to high mountains, because they get as high up in the atmosphere as they can, so they're above. If you go to Haleakala in Hawaii, for example, you're above the clouds, and you can actually get a very nice set of measurements from the top of Haleakala and the top of Mauna Kea, and that's what NOAA do for some of their climate studies. They have LIDARs on those very tall mountains in Hawaii. And then finally, it depends on the size of your telescope. If you think about the LIDAR hitting a target far away, the light coming back to us comes back spread out over a whole sphere. The amount of light that comes into your eye depends on the size of your pupil. If you're in a dark room, your pupils will dilate to let in more light so that you can see something. Well, similarly in LIDAR, the area of the telescope is critical, and again, people with very large budgets will try and create telescopes that are maybe 4 meters in diameter or 12 feet in diameter, whereas typical university telescopes are 1 meter in diameter. But as that telescope gets larger, it's just like dilating the pupil of your eye. You capture more light so that you can get more signal to work with. So those are the trade-offs that we have in LIDAR systems. And again, in different applications, in an unmanned aerial vehicle, it might be that you can work with a very small telescope and a very weak laser because you fly your unmanned aerial system very close to the target of interest. You fly it maybe close to a fire or something that you want to measure. If you're looking into the high atmosphere, you're very far away from your target, and you need large area telescopes and large energy lasers. So those are some of the trade-offs that you have in this work. And just to give you an idea with lots of numbers, I'm just going to pull out one number from all this. If I think about a laser that's sending out pulses of 1 joule, I am actually putting out about 10 to the 18 photons in every pulse. If we think of photons as the little packets of energy that exist in optics or in light signals, if I look at the number of photons that actually come back from a 1 kilometer slice of the atmosphere into a 1 meter telescope from 60 kilometers away, I get all of 3 photons back. So it's a very inefficient experiment. And the reason again for that is I put a huge amount of photons into the sky, they reflect or scatter from some object far away, they scatter in all directions, but I'm only capturing a very small amount of that signal coming back in my telescope. So those are the trade-offs I have. Those are also trade-offs in terrestrial LiDAR about whether people decide to fly low near the ground or fly high off the ground. They trade off. If you fly low to the ground, you get good signals, but you're only covering a narrow swath in your mapping. If you fly high off the ground, the whole survey might be cheaper because you can have a larger swath as you go along, but the signals may be weaker and you may not have the signal integrity that you need to make the map that you wanted, and you have to trade that off in what you can afford and what you're looking for in your mapping. So again, I highlighted just to give you an idea of some of the structures of noctilucent clouds and the fact that they do such a good job of revealing a whole bunch of meteorology as well as interest in the clouds themselves. I'll just go through these relatively quickly. As I say, if you're interested in noctilucent cloud watching, these clouds are 50 miles high. When they were discovered for the first time in the 1870s, people didn't believe the atmosphere extended that high. And Alfred Wegener, who became famous for his continental drift work, actually did triangulations in Scandinavia and reported these clouds as being at a height of 50 miles. What's curious to people from a climate change scenario is these clouds are only reported in the late 19th century, even though people in Scandinavia had been looking at the aurora since the 1500s. And so the thought is that as the atmosphere has increased in carbon dioxide and water vapor, the upper atmosphere paradoxically gets colder as you put in more carbon dioxide. The lower atmosphere gets warmer as you put in more carbon dioxide. And so the thought is that we've had greenhouse cooling in the upper atmosphere and release of water vapor associated with human activity. The trigger for these clouds appearing is thought to be the huge eruption of Mount Krakatoa in Indonesia in the 1860s. There was a massive eruption. There's actually a climate signature from the amount of ash at that time. Volcanoes tend to cool the planet when they erupt if their ash gets into the high atmosphere and it stays there for a long time. And Mount Krakatoa was a climate-changing eruption, and one of its legacies is believed to perhaps be the triggering of large-scale noctilucent clouds. If you plan to be a noctilucent cloud tourist and you want to go out and look for these clouds in August, remember, if you want to see clouds that are 50 miles high, that means there can be no clouds lower down blocking your view. So the sky must be relatively free of tropospheric clouds. The sun must be less than 16 degrees below the horizon, and I'll show that in a cartoon. But the sun must be at least 6 degrees. So there's a sweet point about how low the sun is below the horizon that works for midnight in Fairbanks in the first couple of weeks in August. The clouds are there in July, but the sun is too high. It's below the horizon in July in Fairbanks, but it's too high. The background sky is too bright to see the clouds. You need for the sun to be below the horizon enough that the background sky is dark, and therefore when the light from the clouds shows against that dark screen. And for people who want a geometric slide of that, this is a slide for an example of the ideal place if you want to see clouds that are above Fairbanks. If Fairbanks is here and you want to see the clouds above Fairbanks, you would go down to Delta Junction just south of us and look north. And we've done experiments doing that with colleagues from Utah State, where our LiDAR was measuring the clouds overhead here, but it was people looking north from Donnelly Dome that were able to see the clouds. And similarly, if you're sitting here, the cloud display that you see are the clouds further north. But the idea is that the sun is below the horizon, the sky is dark, and the cloud is just being illuminated and scattering toward you. As the sun sets further and further, too much of the sunlight is absorbed in the atmosphere and grazing the earth, and it doesn't give you enough light to illuminate the clouds. The clouds are only visible to our LiDAR systems in the middle of the night. This goes from 11 o'clock at night to 2 o'clock in the morning, and this gives you an idea of the echo of the cloud. My colleagues who study cirrus clouds, like Ken Sasson, have similar echoes. of cirrus clouds, but what we use these studies for is to understand, does the structure that we see make sense in terms of the amount of water vapor in the atmosphere and the temperatures of the atmosphere. So we use these clouds data sets as a benchmark for assessing water vapor and temperature in the atmosphere, as well as people who are interested in the cloud particles for themselves, and also people are widely interested in just the natural beauty of the clouds. The reason these clouds show up in summer is because paradoxically the region of the atmosphere where these clouds exist, 80 kilometers or 50 miles high, is colder in summer than in winter. And this is of wide interest in atmospheric science because we have a region of the atmosphere climatologically that even though we have 24-hour sunlight in this region in the summer, we have colder temperatures in the summer and winter, and that's why these little ice particle clouds can form. And it's an example of a part of the atmosphere that is not driven by the radiation from the sun. We think of the climate of the Earth being defined by the sunlight being absorbed on the surface of the Earth and that heat going back into the atmosphere. Also that heat being absorbed in the ozone layer, that sunlight being absorbed in the ozone layer, the ultraviolet light. And the ozone layer is warmer in summer than in winter, as we would expect. But paradoxically, we have a part of the atmosphere that is out of sync with radiation. And so studying these clouds and their environment is of interest to people more generally because they're in this natural environment that doesn't fit with how we think about the sun heating the atmosphere. Just to say about how clouds can be used to indicate water vapor in the atmosphere. Any particle, whether it's a droplet or an ice particle or a water droplet, has a vapor pressure around it. There will be some water in the gas phase around that particle based on its temperature. As the temperature increases, there'll be more water vapor around it. So there's a saturation vapor pressure around the particle associated with the particle being present or the droplet being present. There's also the ambient vapor pressure of the atmosphere. If the vapor pressure of the atmosphere is more blue or greater than the vapor pressure around the particle, then water vapor molecules will deposit. They will come out of the air they will push themselves onto the crystal and it will grow. If the vapor pressure is larger than the ambient vapor pressure, the particle will shrink because it will shed water vapor into the environment. If the vapor pressure and the saturation vapor pressure are in balance, then the crystals exist stably, and that's when we have a stable cloud. So if I know the temperature and I say the cloud is stable, then I have a relationship that I can use that relates temperature to the pressure, and I can actually use clouds as a detector of the amount of water vapor present. And that's how clouds are used to tell us about the water vapor in the environment. All I want to point out is there's exponential behavior here with temperature, so it's very sensitive to temperature, and that's actually, again, why the clouds are interesting. That small changes in temperature make big changes in the stability of these clouds, and therefore these clouds become a very sensitive indicator of their environmental conditions. So from there I want to talk a little bit about volcanoes and get to the second topic about volcanoes in Alaska. And as most Alaskans know, we're very proud of the fact that there's 44 volcanoes, I believe, in the state of Alaska, along the Ring of Fire through the Aleutian Arc and out towards Kamchatka. This is an example of the volcano ash associated. This is 100 micrometers. So these are about 1,000 times larger than NLC particles, but this is the silicate ash associated with the eruption of Mount Augustine in 2006. And what's of interest to people, of course, beyond the volcanology is that the aircraft track corridor from Japan and China to the western United States, the Great Circle travels right over these volcanoes. And so the Federal Aviation Administration and others are interested in being able to alert people to problems they might have, because this silicate does a very good job in a jet engine of turning into glass. In the high temperature jet engines, this will turn into glass and essentially stop the engine. And that's what happened in a famous case of a flight over Anchorage, where the plane actually stalled and dropped in the sky, and then was fortunate enough to be able to restart its engines and clear them out, and nobody was killed. But the plane dropped in the sky because it flew through an ash cloud. And these ash clouds, while they're quite visible next to the volcano, as the ash dissipates away, they become subvisible, and they're not necessarily visible to satellites. And so in 2006, there was there was persistent eruptions of Mount Augustine in January 2006, and a bunch of flights were cancelled in Anchorage. They all came to Fairbanks. That made the Fairbanks airport very happy that year because they got all the landing charges for those flights. So there's some economic impacts here in our favor, but generally it was not a good thing. 36 flights were cancelled. And so here's the sequence of events of things that were happening. There was just repeated eruptions of Mount Augustine in late January, and on the 28th of January there were 5 eruptive events with ash getting as high as 30,000 feet or about 9 kilometers. And why that of interest to atmospheric scientists is, at that point the ash is getting through the troposphere into the stratosphere and potentially will be very long-lived. In the troposphere we have weather, the ash will rain out over time, but in the stratosphere we don't have weather in the same way. We don't have rain out. The stratosphere is very stable, the ozone layer is there. Anything that's introduced into the stratosphere can travel for a long time in the stratosphere without being removed from the atmosphere. So as these plumes get higher, their persistence in the atmosphere is also going to increase. So there are several large eruptions, and so at this point the Alaska Volcano Observatory contacted us, Ken Dean, and said, you LIDAR guys, we think there's a possibility some of this ash will come north over Alaska, and if you guys could document that with your LIDARs, it would give us a validation of our prediction and our forecast of where the ash is supposed to go. So we ran out and made measurements, and this is that story of how we did that. So just to give you an idea, when we look at the Mount Augustine eruption, what was interesting about it was it erupted, the ash came south over Kodiak Island, and typically it would drift off out into the Pacific Ocean. And nobody would, and yes, satellites would see it while the cloud was dense and thick near the volcano, but after that it might just be some random occurrence like a commercial aircraft going through a sulfur dioxide cloud, that there might be some complaints about the smell in the cabin. That would be the detection. But what happened in this case is the actual cloud swirled north and came across the state. And by good luck, and totally by good luck, by serendipity, came north across the state and came over a LIDAR in Fairbanks on the roof of the Geophysical Institute run by Ken Sasson, LIDARs at Chattanooga at Poker Flat Research Range operated by myself and Javier Foshisado, and on to Barrow to LIDARs operated by the Department of Energy. And so, just to give you a flavor for that story, there was a whole bunch of monitoring of the volcanoes locally in the Anchorage area with sampling. And so, here are the ash cloud predictions, and here are the predictions for the 31st of January, the 2nd of February, and the 2nd of February later that day. And what the ash cloud is showing, what they do in the PUF model is they take the fact that an eruption has occurred to a certain height, they create a trace of particles over the volcano, and then they see how those particles drift with the wind. And the color coding is different height. The red particles are at 6 kilometers, the purple particles are close to the ground, and there's a rainbow in between. But the idea is that in a single map, they're giving you both height information as well as horizontal spatial information. And so based on this prediction, as I say, we took LIDAR measurements, and the LIDAR measurements look something like this. But again, we have signal with height, but now we're in the bottom 5 miles or 8 kilometers of the atmosphere. And we see, if there was no clouds present, our echo would have looked like this. It's what we call a Rayleigh echo, the echo just from the sky itself. It's the reason why the sky is blue, that the sky scatters light. Up high, there is no clouds, and our echo for the LIDAR matches the Rayleigh echo. But down below, we have extra echo, and all that extra echo is clouds. And so the question is, how do we tease out the presence of volcano ash in all these clouds that are present in the data from 1 kilometer up through 5 kilometers, and actually a hint of extra stuff even up to 6 kilometers. And so how we did this was, that echo represents the echo integrated over an hour and a half that evening. It was an evening we'd normally never make measurements of the upper atmosphere. There was lots of clouds. If I look at how that echo evolved in time over that period, you can see that you have strong echoes are yellow, weak echoes are black. What you have is initially, you can see this is downward moving rain. Essentially it wasn't quite raining, but it was pretty close. Downward moving large particle clouds. These represent cirrus clouds that we see every day, that are ice crystal clouds that generally don't move up and down much. They're just very fine structured and occur in layers. So these are our heavy water vapor clouds. These are our cirrus clouds. And when I blow up the upper altitude region, around 4 kilometers, 4 and 5 kilometers, here's my cirrus clouds blown up. Here's my thick clouds below. I see this persistent echoing that doesn't seem to move up or down at all. And that persistent echoing is the echo from very fine ash particles that are just sitting in the air that are embedded in all these other clouds. And so our technique for detecting them was based on their persistence in all the other clouds that were moving up and down through the night. There was just this persistent echo that was consistent with the ash that had been predicted. And so Ken Sasson was able to come in the next day on February 1st with measurements here in town at the on the roof of the Geophysical Institute, and he actually looks at the polarization of the light coming back. If a particle is small and spherical, the polarization of the light coming out and the light coming back is similar. If a particle is irregular shaped, like a needle, then the polarization of the light being transmitted by the laser and then reflected by the particle is different. And you get what's called a depolarization ratio. Cirrus clouds are famous for being needle-like. And so they have a high depolarization ratio. Ash, which is small, has a low depolarization ratio. So he was able to confirm that what we were seeing in terms of the movement of the ash relative to the clouds and how we were identifying the ash, that was consistent with what he was seeing when he could look at the polarization properties of the ash cloud. And again, the lidars are able to see this in a way that satellites aren't. Because the laser beams are so intense, they can pull out these very fine clouds that wouldn't normally be visible to other methods. And so, to put the whole story together, we combined our work with Kathy Cahill, who was measuring ash on the ground, and based on the chemical composition of the ash on the ground, she was able to say whether it was likely to be volcano ash or maybe it was just road dust. There's a whole variety of dust that she measures in Alaska. She measures pollution, she measures road dust. She also looks for volcanic ash when there are volcanic things happening. And so we combined her measurements to say that yes, in Fairbanks area, we were seeing ash coming out on the ground. That ash was finally falling onto the ground, and it had the signature of volcanic ash. We had light, so we started with a sampler at Homer, saying the ash coming from the volcano has a high iron to calcium ratio. Then we had satellite images around the volcano. Then we had the lidar at Chattanooga showing an echo profile up to 6 kilometers, saying there's ash over Chattanooga up to 6 kilometers. The sampler at Fairbanks confirmed that was at a volcano signature to the ash that was present at the time. Then a lidar at Barrow saw a profile again up to 6 kilometers. And a lidar at Fairbanks saw, again, ash on the 1st of February up to 4 kilometers. And finally, a satellite profile did show some sulfur dioxide over northern Alaska, consistent with the movement that was consistent with the lidar echoes. So we had tracked the volcano cloud across the state at these pinpoint locations, and then our echoes fit with these predictions. That our laser beams coming up through the cloud located the top height of the cloud being at about 5 to 6 kilometers, which is what the the PUF model and the Alaska Volcano Observatory had predicted. So just to say, all those elements coming together, it's not just the single LiDAR measurements at Chattanooga that gave us confidence that we were doing a good job of tracking the cloud, or that the predictions of the Alaska Volcano Observatory were good. It's a key part of this is all those elements coming together across the state. And again, this is all fortuitous. You can't make volcano clouds go across the state as if you're in a laboratory doing a fluid dynamics experiment. It's purely the good luck of the weather systems at this time that carried the ash over the state where there were LiDARs sitting below ready to sample it. The last thing I want to talk about in this lecture is LiDAR for mapping. I am not an expert in LiDAR mapping, but I've followed it in the state. I've given some public talks about it and referring to other people's work. The work I'm going to highlight today in the research results is work from the state government, from the Division of Geological and Geophysical Surveys, and I'll credit that work when I get to it. But the idea of, particularly in a state like Alaska, where we've got lots of land and very little roads, and getting people out to do surveys is difficult. And a lot of our maps are still quite old in terms of the mappings that were done in the 50s and 60s that in certain parts of the state are still depending on. And so in the last few years, huge jump forward in putting lasers into aircraft and using them to map on the ground as they fly. And where our lasers looking up into the atmosphere are getting echoes from very far away, and they're putting out maybe half joule of energy 20 or 30 times a second. These are small little lasers. They have to be small pulse energies because they can't blind people, but they're putting out 33,000 pulses a second, but they might only be putting out microjoules of energy. And you're getting echoes from the ground with a scanning system that fans your beam across the ground and looks at the echoes. You're getting accuracies to about 15 centimeters. And what's made this particularly happen well is not just the laser technology, but also GPS. That GPS satellites can give you such a precise location of your aircraft that you can get truly precise measurements. You may set up a ground station that you've surveyed for your GPS so that you've got an absolute reference here, then the reference to the satellites, and then the reference to the plane, all tied back to this absolutely surveyed reference here in any mapping project. You bring all this together to get very accurate maps. And the thing about this that is, well, let me talk about what's fun in it. There's the boring way to do LiDAR in a plane, which is sitting in what we think of as an executive type turboprop plane. You would have a bunch of big boxes. This would be the power supply for the lasers. This might be the scanner setting with the telescope, and they would sit there and there. You'd sit in the plane, and away you'd go. There's also a much more macho way to do LiDAR, which is done in an example from Switzerland, where you've got very sharp valleys. And so the plane flying along doing this misses the sharp edges of the valleys. Doesn't map the valley edges well. And so if you want to be very gung-ho about it, you can actually hold the LiDAR like this and sit off the edge of the helicopter and map exactly what you want to see, where you as a human are targeting exactly the geological features that you want to see. You're not just depending on a standard scanning pattern. And as I say, the LiDAR came of age because of both lasers becoming more stable, high-speed electronics and computers were a huge part of this, and a mature globally positioning system. All those three elements came together to revolutionize surveying in this way. The following elements are found. You have a laser ranging unit, an optical scanning system because you have to sweep the beam back and forth to make your map, electronic and computer unit, a position and orientation unit, software, and some kind of imaging system. When people do LiDAR surveys, they always take a video record of what they saw just so that they can make human sense of the data. It's not just a blind map pattern from the lasers. Imaging notes just shows the cover of imaging notes from winter 2011, shows the idea that you can go in and you can map individual power lines. So that you can go in and get all the human geography as well as the natural geography and get these very dense maps, three-dimensional maps that then you can bring a whole bunch of computer techniques to analyzing. So it's not like looking at a traditional map and saying, I'm going to look at the transect here, and you get a transect. And that's interesting, and it maybe help you in working out on weekends hiking or something. These are creating very dense data sets for applications in development. We'll see a few in Alaska, in looking at natural hazards and slip. They're being used in agriculture. They're being used in the military. You can imagine the applications in the military. So what happens when a laser beam comes down out of the sky over a small forest? If we think about the boreal forest here in Fairbanks, occasionally the laser echoes will come down and hit the ground. So if your idea is to map the ground, then those are the echoes you want. Occasionally the echo will first come from the top of the tree and go no further. And if you were a forester, those might be the echoes you want because you're interested in tree height, because if you know the height of your trees, maybe if you've got a forest where it's a monoculture of trees, like on a tree farm, the height of the tree may relate very well to the thickness of the diameter of the trunk, and therefore by knowing your tree heights in a planned forest, you can work out actually how much wood is in the forest. You may also be interested in the fact that you've got low bushes and high bushes in the same forest, and this may be an indicator that somebody in Northern California is growing marijuana in the midst of a forest. And you go in and want to do a survey like that without actually having to go in on the ground and potentially get killed by the people growing marijuana. So there's a whole bunch of applications here. But the idea is that you get pulses in a canopy. Your first pulse, it will be a ground pulse, or maybe it'll be the top of a canopy pulse, your echo. Your second echo may be from lower plants, and maybe your third echo from the ground. So there's a lot of intelligence to the interpretation going in blind to a new landscape and surveying it. And just to give you an idea, 16,000 pulses came from trees, the ground, and everything in between. Only 83 pulses, if I go with the pulses that came last, if I say, well, my fourth echo will always be from the ground, I've only got 83 pulses that are laying out the ground. And so there's a lot of intelligence in computer software to looking at a LiDAR data set and saying, do I look at the first echo that came back in each pulse, which is this, the second echoes, which are this, 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 and this, and how do I separate out the canopy echoes from the ground echoes? Is my application to do a ground mapping, or is my application to look at the high trees, or is my application to look for those lower trees that maybe shouldn't be there, or those lower plants? And so there's a huge amount of, this is what's made these data sets useful, just like in genetics. It's not just the biology, it's having the computers that can actually probe the data sets, because you're not going to do any of this by hand. You're not going to have graduate students and yourself sitting, going through this, cherry picking the data. You're going to have sophisticated algorithms for sweeping through these large data sets. I just wanted to highlight that work in Alaska, the role of the university has been to provide quality assurance for LiDAR maps. So what's happened in, for example, places like the Kenai, one of the first places to do a LiDAR survey was the watershed people in the Kenai got the money to do a LiDAR survey. They contracted with a commercial supplier of LiDAR, Aerosense, down in Anchorage. And then they asked Rick Gertz at the Alaska Volcano Observatory to provide an independent quality control. And they went back and forth a few times between Rick and their aerometrics to go back and forth, looking at the data and make sure the data had been analyzed the way they wanted. But as part of that, Rick set up an actual survey point, and this just shows you coming at this building, gives you the density of the LiDAR data sweeping across in different directions, but having this data point in the center that's an absolute reference, and doing that kind of quality assurance. It's interesting that as surveys have continued in the state, people have continued to retain the university, but commercial vendors increasingly ask the university to do less and less. And so the university in the beginning was empowering these kind of surveys quite a bit and doing a significant amount of work, and now as people have become more LiDAR savvy, they're like, okay, well the university can do its thing, but we want more of the contract. And that's just sort of a natural evolution in how these things develop as they become less research driven and more mainstream. The thing that the Division of Geological and Geophysical Survey is doing is looking at earthquake hazards. And I'm not a geologist, but I'll just highlight, give you a flavor for what's happening. This work was done by Rich Kohler. The particular example I'm going to talk about is the Castle Mountain Fault Study area just north of Anchorage. And Rich and his colleagues presented this work as a poster at the American Geophysical Union in December 2012, just a couple of months ago. And I just want to highlight what they're doing. As I say, if there are any of you have geology backgrounds, you probably have a better understanding of this than me. But we're looking here at the Castle Mountain Fall. The Little Susitna River is here. And what we're doing is, this is the photography survey. Then this is the same thing in Lidar echoes. And then this is the same thing in terms of a geological map laying out the different ages of the rock that are there. And this represents 5 kilometers. What happens with the Lidar is you can begin to see just how detailed some of the mapping really is in the Lidar, the details that you're picking out. And so what Rich and his colleagues did was go in and look at these small sections that are about 1 kilometer square and use the Lidar mapping, which is very dense, to assess slippage, geological slippage in the earth and what the earthquake hazards were. So they took these areas and blew them up even more and looked, essentially, because the Lidar data is so rich, no pun intended, that you can go in and look at slippage in very fine features and look for patterns of slippage through these different test areas. And this is what the terrestrial Lidar does very well. And what they actually found, I just want to highlight the result, was they actually found that the displacement rates were much less than had previously been thought. They were able to reassess the geological hazards. They use a slip rate of 3 millimeters per year for the Castle Mountain Fault area, and in fact they were able to show that the displacement was much less, at about 0.5 millimeter per year, or even less than 0.3 millimeters a year in some cases. They were able to reassess the amount of slippage by a factor of 10 by having these very dense Lidar maps where they could really look at how the material surface is slipping over time. This work has been done also in support of the Alaska Gas Line Development Corporation, because these hazards are being mapped in response to assessing running a gas pipeline from Fairbanks down to Anchorage, or running gas pipelines down through the Alaska Highway Corridor. In the work with the Alaska Highway Corridor, this is, first of all, looking at the map from Google Maps. This is Delta, this is the Alaska Highway, and there's the little, I think the Johnson River is here, the little Gressel River is here. Turning the view around in the other direction, this is the Lidar map, and here's the highway. And what's of interest to the people in the geological survey is the amount of detail showing where geological formations come out under the road, where the road is built on top of formations, and where this very deep structure associated with with what appears to be geological movement under the highway here. But this is revealed in the Lidar data in ways that it's not revealed in the ordinary surveys. So, in finishing up, I'd just like to say that Lidar research at the University of Alaska Fairbanks is done by a whole variety of people. I won't go through all the names, but we have people mapping glaciers, we have people doing terrestrial mapping, people in the atmospheric sciences, and people who are interested in using Lidars on manned aerial vehicles. I hope I've given you some flavor of the diversity of applications in the state, from gee-whiz natural phenomena to places where transportation and safety are an issue with volcano clouds, and also looking at where Lidar is actually being used in surveying the state and creating economic opportunities in the state. Thank you.